you. Thank you for coming back. Today is the last talk. And today I'm going to show you again an application of dynamics of homogeneous flows to problem a number theory, use Frobenius numbers, and a related question on circular graphs. And I'll show you what these are. But let me first give you a little motivation and background. So, of course, graph theory and network theory is now an extremely popular topic because we're now actually dealing with huge networks like the internet and social networks and so on. And so the question is, when you are faced with such a thing, how can you describe it? And that means in terms of simple numbers, right? So one thing you would be interested in is to ask how connected is a network? And what are the distributions of the nodes? You know, how many friends does a person have with a certain probability? Questions like this. So in other words, when you have these huge networks, you want to find a few numbers that actually tell you something about the structure of these networks. And we are going to talk about the diameter, one example of such a characterization. So the diameter of a graph, and by graph I just mean you take a collection of points, you call them vertices, and then you prescribe which vertices are connected. And these things are called edges. And here, so the beautiful thing is if you now have any of those algebra math programs like Mathematica, you can generate all of these things, and that particular command finds you the diameter. So what's the diameter of a graph? The diameter of a graph is the largest distance you can find between any two vertices.
Take the points in the Euclidean space?
No. So, it's a good question. What does distance mean, right? That's your question. So distance here means each vertex that's connected to another one, these two will have distance 1. Okay? And then the distance between more points is described by simply looking at all paths that connect the 2 points, and you take the smallest, and that's your distance. Now you can weight things. So you can also say, well, I don't want to take this to be 1, but you assign to each edge a weight, call it the length, and then you have another metric, and you can minimize with respect to that. Okay, so this is what it is. So if you like, you can also embed it into the Euclidean space, as you say, and take that as a metric. It's fine too. Everything's allowed. And in fact, you know, one of the nice questions in these kind of problems is to have 2 different metrics and see how they sort of relate to each other. Okay, so that's the question. And why is the diameter an interesting quantity to consider? Well, you might all have heard of the small world phenomenon, that we all know each other through at most 5 or 6 neighbors, and this phenomenon in a mathematical sense is characterized in the following way. So, what does it mean to have a small diameter? Well, for a kid's graph, it doesn't mean anything. So when you actually want to compare it with sort of real-world networks that have millions or billions of nodes, what you want to do is you want to come up with a mathematical model that doesn't just contain of one ensemble of graphs, but a sequence of graphs whose number of vertices goes to infinity, n, we call the number of vertices, and what you'd like to observe is that the diameter grows logarithmic in n, slowly in other words, right? Then you say, okay, for this sequence of graphs we have a small world phenomenon. And
so you're making a definition or you're making some statement now? About this are very different graphs.
I'm making a definition.
And saying which.
Yeah. So I'm saying definition, I'm calling a sequence of graphs to show a small world phenomenon if the diameter grows like the log of the number of vertices. And a very important and popular article in this field was by Watts and Strogatz, who designed a very simple model how to observe such a phenomenon. So let me describe this to you. You start with a regular graph like this. This, by the way, is a circular graph that we're going to meet later. One particular example. So this is very regular, right? So you just put the n vertices on this circle and you connect the nearest neighbor here and then the next to nearest neighbor. That's it. So you start with this. Now you start removing edges with probability p and you reassign them randomly. Okay? You do this. Now what they observe is that when p is 0, this thing, obviously, the diameter grows linearly in n. Does everybody agree with that? Right, so as you expand, it grows linearly.
Well, what is that? You're just... What are the edges there?
The edges are the lines drawn, right? So you connect. So we put all these guys in a circle, and then you connect the nearest guys. So there's an edge here, and then there is an edge to the next to nearest guy. Okay. So what is the pair of vertices that realize the biggest distance? They're basically opposite of each other, right? Yeah, everybody's happy with that, right? And so what's the diameter therefore? It's roughly n over 2. It depends if it's even or odd. Right, so it grows linearly in n.
Wouldn't you use n over 6 or something?
Hmm? Yeah, because we do nearest neighbor. Comes up to constants. Okay? You're right. It would be n over 2 if we only had the circle, but because we do this, we have... Well, you can compute it. Tell me afterwards. Anyway, statement is it grows linearly in n. Some constant times n. Now then we reassign edges. So you can think a friendship breaks up, right? And the guy gets a new friend over here, randomly assigned. What they observed is that if the probability of reassigning an edge here at 0 becomes some macroscopic value, then you see that the diameter grows like log n. Numerically, right? As
soon as what? As soon as the probability is what?
Say it's a half. Say it's 0.1.
0.1.
Anything positive? Or is there a critical value that has to be?
I have no idea. I'll tell you in a second. I have no idea what the probability is. These are just numerical experiments, and I'm going to tell you in a second what is non-rigorous in there.
So each graph, so you apply this random assign once and then look at the graph each other.
You look at each edge, you throw your dice, or your coin. If you get heads, you remove, and you reassign. If you get tails, you keep it as it is. You do this for every edge. Okay? Okay, so all I want to say, this was an important paper. Surprising, there was a paper by Bolovas and Chung, which had almost the same model many years before. Of course, these guys are well known, but they didn't become the superstars of Watts and Strogatz. Everybody's talking about the Watts-Strogatz model. But they had almost the same model. They looked at a cycle of length n, and then they added random matchings. And they actually proved that the thing goes like log n time. Almost surely. Okay? In gray, I have lots of other papers who prove very similar things. Shireni, random graphs, and so on. But I'm just highlighting the ones that are sort of close to the small world phenomenon, small world models that physicists have come up with. And here's another one, Bolovas and Hiroda, who studied the so-called Barabasi-Albert small world model. And you see what they proved is actually that the growth of the diameter is even a little less than log n. So these are the results, but I'm not going to talk about this. I don't have anything to say. Just the motivation and the background. What I want to talk about are these circular graphs. And let's just look at how the diameters grow for these things. So this is the problem. And now how is a circular graph defined? So let me give you a simple example. Let's fix A1, A2. Let's say A1 is 2, A2 is, shall we say, 5, and A3 is, I shouldn't get something on this. Otherwise I have to draw forever. Let's just take 2. So what does it mean? Let's take n equal to 10 vertices. That's that. 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 9. Okay. I want the, as you will see in this construction, I want the GCD of those three numbers to be 1. Otherwise I would get something disconnected. Okay. So how do I construct now a circular graph? Well, I say I connect two vertices, I and j, if their difference is congruent to one of those numbers, modulo n. Okay? So here, a1 equal to 2 would mean connect all guys that have distance 2. So here I'll just number them 1, 2, 3, 4, 5, 7, 8, 9. So 3 minus 1 is 2, that's good. So I'm going to connect all those guys. Tell me if I'm making a mistake or if I forgot something. So I've got like this. And then I have to do 5. So, so now 3.
And it's not right.
No, this I want this condition, right? Not pairwise, just the whole. Okay, thank you for pointing this out. It's great. I always get these things mixed up. Okay, so let's do the same. So now I have to connect 4. I get this. And so you see it's a very simple construction. You have to shout if I get something wrong because I can't say anything here. What do I have? 6 to 9. 6 and 9, yeah. And 7 and 1, yeah, is that good? And 8 and 2. What have we got here? 3. Yes. Yeah. Is that good? Yeah?
Yeah.
And then I have this one. Anything missing? Okay. So that's the construction. That's a circular graph. Okay? Now, I'm surprised this thing always switches off. Alright, so here's another example. With those numbers, 1, 15, and 20, and n is 41. And my little Mathematica command line here highlights a pair of vertices, this and this one, that realize the diameter. So what's the diameter here? 1, 2, 3, 4. Yeah? So it looks complicated. And the question is, how can we calculate this diameter? And now these networks are also called multi-loop network, or they are an undirected Cayley graph of the cyclic group. And in computer science, people are interested in this because they like these. If you do some parallel processing and you think of your nodes as processes, and you want to sort of connect them up in an isometric way so that you have reasonably high connectivity. Of course, a real network, I would say, well, you should connect them up really in a random way. That way you get much better connectivity, but then, it looks maybe ugly. So here we are. And now the question is, well, how does this diameter grow? And what can we say exactly precisely about its size? Now my point of view here was to observe that when you change the AJs, the diameter will actually fluctuate dramatically. So it makes sense again to ask, well, first of all, how large is the diameter roughly? And then second, can we say something about the distribution of its values as we vary these connection numbers over a large set? Okay, and this is what this theorem says. So we want to look at an ensemble, as people do in general for random graphs. We want to generate an ensemble of random graphs, and we do this in the following way. We take some set, and again, just take a ball. This is my set D, and then you make that ball very large. Okay, so this will be TD, where T tends to infinity. And we look at all primitive lattice points. Primitive because we assume that the GCD has to be 1, as I mentioned before. If we wouldn't have this assumption, we would get a disconnected graph, so the diameter would be infinity. So that's not good, right? So the GCD equal 1 ensures that we have only one connected component. And we throw these just at random in this big ball. And then we say, do we have a limit distribution? We pick them with equal weight. And this theorem says yes. Okay, so this theorem says yes. If we normalize...
So you only have one A and one N?
Mm-hmm. So here.
So the previous example, when you took 2 and 9, 8 is a vector.
Huh?
8 is a vector. 8 is a
yeah.
vector.
So A is a vector. So A is a vector, in this example, A1, A2.
I'm still worried because 2 and 9 are relatively prime, but it was disconnected. It seems strange.
What? No. Yeah, so here the GCD is 1. Huh?
Good. Forget the A2 part, that was the pink.
Yeah, okay. If you forget the A2, if you forget the A1 part, you see it's disconnected.
It should be disconnected.
Yeah, look at it. That's just the red bit, right?
Okay, fine.
Have a look.
It is.
You see the two components. It's disconnected.
Disconnected.
But then, if you do that, then the whole thing becomes connected. Okay, so this tells you that if you normalize, and this is the important thing here, remember for small networks we would think the diameter grows like log n. Here the diameter will grow like n to the 1 over k, where k is the number of connections you make, right? 2. And so this converges in distribution as a random variable to some limiting distribution. And what is this limiting distribution? How?
With L.
Oh, I'm sorry. Yeah, I didn't really explain this very well. So I do exactly what you wanted me. Put a little more interesting metric on it. So I'm going to say L is the vector of length L1 for my L2. Other way around. This should be white and this should be red. Right? So that the white edges have length, they all have length L1. The red edges have all length L2. Just take them to be 1 if you want. I need them later on for my application to this other problem that they can vary them. So just put a metric on this graph, and you just decide that for different connectors you have different length. Okay, and then you can calculate the diameter for them. As I said, this thing is wildly fluctuating, and it converges to some limiting distribution. And an important observation of this theorem is that this limiting distribution here doesn't depend on D, on the set that I've chosen. So if I would take another set, something like this, and expand it, it would look like that, right? And take the A's at random with uniform probability from that set, the limiting distribution would be the same. And that is an important question. I just want to highlight this because you can also look at the value distribution of very many non-random things. So for instance, you can just take a grid here, and then you look at some fixed function, continuous function over it, and say, you ask what's the distribution of values of this function at the integer lattice points in some fixed interval, you'd get some answer, right? But this answer would depend if you would pick them at random from this stretch, or from this stretch, or from this stretch. If the answer is independent of how you pick them, how you choose your set D, it means this thing is really fluctuating wildly, and sort of things become independent in different patches. Yeah? So this is an important point. Right, so how does this thing look like? And it looks like a nice distribution. Look, that's when k is equal to 2. And here's the formula. And we haven't seen this formula anywhere before. It's not one of the standard distribution that people deal with. And I'm going to show you where this thing comes from. Of course, you already smell a rat, maybe, because in arbitrary dimensions, we can show that this thing, again, has a heavy tail, polynomial tail. It looks a little similar to what I showed you yesterday. And it will turn out that these things are actually related to what I've talked about in the previous two lectures.
So what is the distribution shown on the graph? The distribution of what?
It's the limiting distribution. So this thing converges to some random variable, and I'm showing you the density of this random variable. Right? So it's the probability density that describes the limiting law. So if you'd had a central limit theorem, you would get a Gaussian distribution here. But we don't have it, right? We have this as the limiting distribution. And again, you get Riemann zeta. So let me show you what the answer is. And there you go, right? The random lattices appear again for some reason that I'm going to show you why. So this random variable here is the following. It is the covering radius of a random lattice L in Rk with respect to this polytope. So the covering radius is it's a very important notion in the geometry of numbers, and how is it defined? In the following way. So what's a covering radius? You take some convex set K, and now the covering radius is the smallest dilation factor that you need so that the translates of this expanded or shrunk set K cover all of Rk. Yeah? So obviously, you know, at some point, so you have...
Translate by what? By the lattice?
Translate by the lattice. Yeah. With respect to L. So you take your set K, right? Look at all its lattice translates. That's a periodic set. Now, if that already covers Rk, you say, okay, I have to shrink K a little bit. You want the smallest K so that it just covers Rk. It could be too small, right? It doesn't cover it, so you need to expand it until it covers everything. That's the covering radius. And you all know the next line, but I just want to remind you again, what's a random lattice? Again, we take a linear lattice of covolume 1. We parameterize the space of all such lattices by SLKR, modulo SLKZ. We have a parameter on SLKR, which we can normalize to become the probability measure on the space of lattices. Okay? So, what I described before, the limit distribution is independent of D, and with this normalization, remember maybe, let me go back. With this normalization, actually the answer is also independent of the metric that you're choosing. Right? The choice of L doesn't appear in the limiting distribution. And now we can use this formula here, when k is equal to 2, to calculate our to calculate this thing. When k is 3 or higher, it's impossible. We only get these asymptotic terms. The geometry of the modular space is just too complicated. The fundamental domain is complicated. I mean, it's known with the computer, but we just can't integrate things by hand. We can do it on a computer, but not by hand. Here, in 2 dimensions, we can do everything by hand. Okay. Next remark. These lengths can actually be functions of n and a if they depend on that in this way. Limit distribution of these parameters. And in fact, when I started this work, I wasn't aware of this conjecture. I just found when finishing the paper, I just found that actually people had asked this question, so that's even better, right? Someone asked the question and you can answer it. And how do we prove this? So now I'm going to show you again how we translate this problem. Just as yesterday, how can we translate this problem into a problem of equidistribution on homogeneous spaces? And here's a quick outline of the proof. So the first step is that you can identify circular graphs with lattice graphs. So this means the following. As you can define a torus as the quotient of Rk modulo a discrete subgroup of Rk, you can construct these circular graphs, in a sense, as discrete tori by thinking now of this as your replacement of Rk, that's now Zk, with, you make it a graph by saying nearest neighbors are connected. So that's now an infinite graph. And then you take a discrete subgroup of Zk to start identifying points. Right? So that's like a discrete torus. Now, circular graphs are special discrete tori with certain extra conditions. And I'm going to show you a little more about this. Now then, when we are interested in the question of the asymptotics for large n, large number of vertices, what you can show is that the diameter of these discrete tori is approximately given by the diameter of a continuous torus with respect to the L1 metric, the Manhattan metric. Because here we only can go up and left, so also in the continuum limit we keep that. And then finally, what we need to show to prove our limit theorem is that the tori that we get from the circular graphs become uniformly distributed in the space of all tori, which is the same as the space of all lattices. That's the strategy.
How do you get a tori from a circular graph?
So let me show you this. Okay, that's the first step. So Zk is our universal cover, if you like. And we define a metric on it just in this way. Right? So that's exactly the way I've drawn. So nearest neighbors are connected only horizontally and vertically. And this is exactly the metric that gives you this. And because we also wanted to have different lengths in the different directions, I'm having this scalar product here with this vector of L's, yeah? And so then this will be a lattice graph, where in the horizontal direction, the length unit is L1, and in the vertical direction, the length unit is L2. And now, I need to define the right subgroup of Zk that gives me a discrete torus that has exactly the same connectivity as the circular graph. Okay, and this is done in the following way. So, let's start off with this line. So that's Zk times Nz. So here, so I'm going to do a little trick now. I'm going to first add a dimension. So this is my old guy here, and then I'm going to add a dimension, Nz. And I will now apply our old friend, the unipotent guy, to shear this. And then I'm going to project the whole thing back down onto zk in this way. So this will now be a sublattice, this NA0, which is just take this, sorry, where is it here? Take this subgroup of zk plus 1 and just look at the slice in the hyperplane that goes to 0, and that again will be a sublattice of index n and zk. I mean, you have to do a little computation to see that.
I didn't understand the statement you're trying to achieve by this argument.
I'm going to show you. So I want to show you how you. So here we have our discrete plane, if you like. So that's our lattice graph. And now I want to show you a torus on this space. Maybe it'll look like this. These two. And these two. This would be an example with a number of vertices in here. So this is a finite torus that you get by identifying all points using these two basis vectors. Okay? And what I'm saying is, how do you have to choose this sublattice so that the graph you get is a circular graph?
So what?
The graph that you get here should be isomorphic to a circular graph. That's the aim.
What graph do you get here? What graph are you referring to?
Okay, the graph that I'm referring to is a graph where edges are connected vertically or horizontally. Okay? And points are identified. So this point will be identified with itself, right? So if you move here, sorry, that's wrong. It will be identified with this point, and with this point, and so on. Using these basis vectors. And so, what I'm showing here is zk modulo some discrete subgroup, which I'm calling lambda na. 0, unfortunately. So I want to show you that if I take my circular graph here, well, this is isomorphic to such an object.
That's been defined by those A's. I forgot what the circular graph is. It's defined by those A's, right?
Yeah, it's defined by those A's. So this is what I want to show. I want to show you some isomorphism in these two things. Because it's not going to be easier to calculate the diameter on this guy than on this guy. Yeah?
So the right choice. So you consider just Z here is a standard lattice projected to some at least a code for that's what that's a graph here.
Now I'm going to show you the construction, how to construct this.
But what is it?
Yeah, we don't understand the statement. So what is G?
You understand?
How does it have a statement?
This is the statement, okay? That these two things are isomorphic. So if I want to calculate the diameter of this, it's the same as calculating the diameter of that. And this shows you the construction on how to get the left-hand side. The right-hand side, you remember, right? What that was. It was just our circular graph.
So but your graph now, graph on the left-hand side is eclipse on some discrete torus, and it is just the standard lattice projected to this torus.
So the point is, if you like.
Oh, did you say yes to this question?
Yes.
Is the standard lattice projected to that torus?
The quotient modular L
It's the standard graph modulo this discrete subgroup. So, in other words, we're looking for the universal cover of our circular graph and try to compute the fundamental group of it, right? And the fundamental group, if you like, is this guy here.
I don't like that statement.
You don't like it?
Not that statement. It's scene, sure. But I mean,
What is
it doesn't matter.
It's very easy, it's very simple. The whole thing. But it's, again, one of the key steps, right? That people
The L's are kind of irrelevant here. The L's are kind of irrelevant. It's like frosting on a cake.
Exactly.
The combinatorial state.
Exactly.
We're trying to get from the combinatorial state.
Exactly.
The standard cubical or square graph projects to this funny torus to be your circular graph. Combinatorial. Is that the statement?
That's exactly the statement. Let me say it in another word, in another way. But you have to sit down at home with a piece of paper and just do this construction. So you really take this lattice here, look at its section that goes through 0, and you get an object like this, okay? And then you want to see which points are connected to it, which other points, and rather than drawing your vertices on a grid, you draw them just on the circle. And then you make all the connections, and you see that the two graphs are isomorphic. Okay?
How do you order the points? Draw on the circle.
So somehow
If you're home with your piece of paper.
the ordering is just given. So somehow using this extension here, I can't describe it so quickly. I could have spent about 20 minutes going through every step. But it's quite nice. You have to believe me now. And if you like, afterwards I can go through it. But that's the point. Yeah? So we have mapped our circular graph onto a finite torus graph.
I know this psychologically between here. Any graph can be drawn, it looks like a circular graph. You just put the vertices on a circle. And you draw the edges, it looks kind of like one of these things.
No, but that's not true, right?
No,
because it has to have this rotational symmetry.
Right, but I mean...
I don't say circular, I say circulant. Right?
Yeah,
because
I know. Any graph sort of, I say circular.
Yeah,
Any graph is sort of circular by drawing vertices on a circle. You see, that's just an extra feature. You're saying that this circular graph is combinatorial to the same as this projected graph.
So but the point is that look at the red and the white guys.
Yeah.
You think of them as living in different dimensions. Okay, so in this case here, I want to identify this with an object that lives in 2 dimensions. So the red guy is 1 dimension and the white guy is 1 dimension. And that's exactly what's generating my lattice Z2. If I would have 3 connections here, I would go into 3 dimensions. And because everything's nicely translation invariant, the rotation here by the red guys becomes the translation in one direction, and the other guy becomes translation in the other direction. That's the idea. Okay. Okay, so that's the first step. The second step is to approximate the diameters of these discrete tori by the diameters of the continuous tori. And so what's going on now? What's going on now is that basically you make this finer and finer, this grid, if you like. You scale out, and you look, the number of vertices increases, so the index of this lattice subgroup still has to be n. So I'm looking here now at a scaling where I basically keep that fundamental domain macroscopic, and the lines here become finer and finer. And so they approximate R2. And you will all believe me when I say that the distance between 2 points here will be approximately, up to an error which is on the scale of the lattice spacing, the same as the continuous distance, but L1, right? And this is what's written down here. So now here, take a Euclidean lattice in RD and define the diameter to be the maximal L1 distance between 2 points on the square torus. This guy here is again a diagonal matrix, which, as you can see, sort of zooms in, right? There is the factor of n there. So each side, n is now plays the role of a volume. So each direction is rescaled by n to the 1 over k. And now pick this particular lattice. That was the subgroup that we had in this construction, and all this matrix is now doing is the zooming in. Okay, so we have this matrix, and then you have this inequality. So this is the diameter of the guy that we're interested in. They'll always be smaller than the diameter of the continuous guy, and up to a small error, the diameter of, again, of the continuous guy. Right? Because the error will be on this scale of the lattice.
The diameter is always this L1 vector.
Always with respect to the L1 vectors. Okay, and then the third observation is that the diameter of this Euclidean torus is exactly the same as the covering radius. It's just a fact, right? Something you can convince yourself.
Why is the L1 metric well defined on the torus?
Why is it well defined?
L1 uses the x and y direction.
Exactly.
But why is that well defined on the torus? Who could probably understand that?
That's a good question. Why is that well defined? Maybe. Okay, I have to think about it. Certainly the diameter is well defined.
What does it mean?
The diameter is well defined, and okay, let's write down. What is it?
Well, go ahead.
So it's the increment.
You can always reduce the metric down.
Yeah, so it's
No, the torus downstairs is, different fundamental domains get the same torus.
You just start with the L1 metric when you leave space and then collapse under an arbitrary ladder.
Shall we do it afterwards?
Yeah.
Otherwise I won't
Yeah.
go to the end. So certainly the diameter, you can see from here that it's well defined. Because the covering radius of the lattice is well defined. And just changing points in the lattice, that's the SL2Z action, right? That messes things about. That's well defined. So that works. That's certainly true. Right. And now, where are we? Well, what I've showed you here is that this lattice here exactly corresponds to the circular graphs, and we throw the AZ random. So we again have a random lattice, but this time it's not a random rotation or anything like that. It's a random unipotent, but along a discrete orbit. And so, just like yesterday, where we used the equidistribution of large spheres to prove our limit theorem, here we will prove the equidistribution of those particular lattices in the limit when n tends to infinity to show our limiting theorem. Right? So here, what does this mean? Well, we sum over all the points in our big expanded set with respect to some test function. So that's exactly the analog of our previous integral over the spheres. And that will converge to the Haar measure on the space of lattices. So that's something you prove. And what I use in the proof of this is, again, the equidistribution of horospheres in these spaces, and realizing that the points that you sum over here are rational points on the horospheres. And this is, of of course, a much more singular average, but you can use a nice geometric argument to show that still these points become uniformly distributed in the right space. And that then shows what we wanted to show.
So you're basically using just the rigidity for the flow?
No, it's not good enough, no. It really, and here the basic fundamental fact is the mixing quality that you need. And Han Li, a student of Marklof, was able to control the rate of convergence of this if you choose your test functions to be have certain smoothness properties. And more recently, so note here that we're summing over A and N, and more recently, Einsiedler, Moses, Shah, and Shapira have refined the theorem, the previous theorem, by not requiring to sum over N. So in the language of these graphs, you actually don't need to take the number of vertices to be random, you can just fix it. And they use Ratner's major classification theorem to get this proof. While in my theorem, I only use the mixing property. So this is a much deeper fundamental statement. Right, so that was what I wanted to talk to you about the circular graph. So now I'm switching to another problem, number theory. Very old, very cute problem that maybe some of you have seen before. And then I'm going to show you how that is related to our diameters of circular graphs. Okay, so what is a Frobenius number? It's also sometimes called the coin exchange problem or the postage stamp problem, and it's one of these challenging cases. So people in integer linear programming are interested in this because the challenge is here to find an algorithm to compute this Frobenius number. So what is it? You start with a integer vector. You assume the coefficients have GCD1 because otherwise the problem would again be sort of trivial. So that assumption you need. And also you would like that each integer is at least 2. Again for trivial reasons, as you can see in a minute. So what's the problem? So we now have this integer vector, primitive, every coefficient at least 2. And we want to understand the set of all non-negative linear combinations, integer linear combinations that you can form with this vector. Right? So all m dot a, but the m are non-negative integers. So it's a known fact that for fixed a, there is an integer, so that all integers that are greater than that integer can be represented in this way. And no gaps anymore. And the largest integer that you cannot represent is called the Frobenius number. And the question is, how large is that? How does that depend as a function of a? So here's the formula for it. Not a formula, a definition. And this is no problem. It goes back to Sylvester, the days when it actually wasn't called the Frobenius number, because Sylvester just calculated this formula. And we let our undergraduates prove this formula when you just have 2 a's, a1 and a2. But already when you go to 3 dimensions, the whole problem becomes much more complicated. There is no such nice explicit formula for the Frobenius number. And there's a first paper that is still at the heart of many other works that are written about this, by Brouwer and Shockley. So Brouwer was a student of Schur, and Schur was a student of Frobenius, and Frobenius had mentioned this in his lectures, and then Schur had explained Brouwer how to write, to get this first algorithm in the 3-dimensional case using continued fractions and a nice reduction. And so eventually Brouwer and Shockley had written this up, and then there are a number of other papers. There's a whole book about this.
What did they do?
I'll come back to this.
Is it sort of cubic?
I'll come back to it. And this is Alfred Brouwer, is not Richard Brouwer, who was his brother. So Alfred was the less famous richer is the more fancy. And I got into this because I've seen a paper by Sinay and Bourgain, I'll mention this in a second, who were in turn motivated by some work of Arnold, who got interested in this. He called this arithmetic turbulence. So he wanted to understand how this Frobenius number is fluctuating. Okay? So you just plug in these values and it's a wild function, and he wanted to understand this. You have sharp up and lower bounds on this number, and there's a whole book. So if you want to learn anything prior to this talk, you should go into study this book. So here's the theorem. Again, in the spirit of Arnold, we ask, how does this thing fluctuate? Right? So what does this mean? Well, you just look at a random argument, and you want to understand its value distribution. So you have to divide by the right normalization, which turns out to be this quantity, and this theorem says that in distribution we're converging to the covering radius of a random lattice L with respect to this simplex. So before it was a different polyhedron.
It was 60 degrees to 3.
Other than that, it's the same.
All those are square root.
Yeah.
Square root.
Yeah. Okay. Yeah, so you remember the explicit formula for d equal to 2, right? Then it would assume you have nothing, right? A1, A2. And you remember that the formula of Fa was A1 times A2 minus A1 minus A2. So that just kills the main term. So there, if you normalize, the Frobenius number, well, this ratio is just 1. So there the value distribution is just a delta function at 1, delta mass at 1, right? In any higher dimension, it's this thing, and in fact, one can show that the density is a nice continuous density. So only in d equal to 2 it's something singular. After that it becomes something else. And people have done numerics with this. So for d equals 3, Bourgain and Sinay proved such a theorem, and in higher dimensions they couldn't quite do it. Sure, Sinay and Ustinov also found an explicit formula. Here I'm showing you numerical calculations by Andreas Wilbergson, who just used the description in terms of random lattices to make these plots. Okay, very easy, they look like this. And again, you can calculate things when you have 3 variables, and in higher variables, Andreas Wilbergson calculated these tables. Okay, so this looks very, very similar.
What's T?
T is a variable.
T is a variable.
Very good. Yeah, this should be T here. Or T should be R. So, why does this look so similar to the circular graphs? That's the question, alright? It's almost the same distribution, just that I'm not taking the covering radius of this polyhedron, which would be a square, but I'm looking at a simplex. So what's the difference? So this was Brown and Shockley's main observation, which, as I mentioned earlier, was later used by others to devise continued fraction algorithms to calculate these things. So what's the idea? Well, the idea is you reduce the question modulo AD. So AD is one of the coefficients that we have, A1 up to AD. And so you basically say, well, let's define f sub r to be the largest number that doesn't have a representation in this set. Yeah? And so the original Frobenius number is just the largest that you get by taking the maximum of all these FRs. Now, how can you now find a simpler formula for these FRs? Well, take the smallest positive integer that has a representation in R modulo AD, that's this guy, NR. The smallest guy, smallest integer, that will be an integer, that has a representation congruent to R modulo AD, and then you can convince yourself that this FR is equal to NRA minus AD. Right? Because you just need to drop by 1 here to get this. Okay. And now the point is, but now we can reduce the whole dimension by 1 because we can find a nice formula of NRA. So you somehow step down by 1 dimension, and that's the reduction that Gao and Shockley found. That's basically the point of their paper, that you can now write that NRA is calculated, it's equal to AD if R is congruent to 0 mod AD, and otherwise it has this formula. Okay? And so, if we put everything together, we get FA is congruent to the maximum of these NRAs minus AD. So, why? So now maybe some of you already see what's going on here. If you remember the definition of the diameter. The diameter was the largest distance between any pairs of vertices. And what's the distance? The distance is the minimum of something, right? It's the shortest path that connects these two. So, as I'll show you now, is that this is exactly the structure that you'll see here. So, the diameter is the maximum over some minimum. This will be realized as some distance, and this will simply be the largest. And before I do this, let me just show you 2 pictures. One is diameters of random circular graphs. You've seen this before. And this guy here is a directed random circular graph. And this looks exactly like the distribution of Frobenius numbers. Oh, okay. That's the problem. I've just jumped over a slide. I'm terrible. I was missing that slide. Sorry. I've given everything away now. So, what I want to show you now is that the Frobenius number can be written, as I explained before, as the diameter of a directed circular graph. And why is it directed? Well, if you look at the previous slide, here, what are these guys? These are exactly paths on a circular graph, but we're only allowed to go in one direction, because we're only allowed to pick non-negative integers, right? And that's why this thing is a direction. It uses a direction. And if you can think about it a little bit, this exactly gives you the correspondence between the path and the directed graph. And that observation is actually old. I wasn't aware of it when I did all this. So I first proved the Frobenius number theorem just by staring at it, basically, and having no connection with the graphs. And then later I found this work of Nienhuis, who explained that actually, to calculate the Frobenius number, you just put it into this geometric picture of directed graphs. And then I thought, okay, so we can actually also say something about directed circular graphs, but also about undirected circular graphs. So actually I've told you the whole story now in the opposite chronological order that I actually had. Now, the only thing here is, as you can see, I need to weight my length. So I can't take length here. So the notation here was, A was the number that connects, that gives us the connections, and L were the lengths. So if I'm choosing A1 to be 3, I need to weight that edge also with a factor of 3. It has to have length 3, okay? And that's why I was insisting in the beginning that I'd like to keep my length variable. And I was insisting that the limiting distribution is independent on how I choose my length if I just normalize correctly. And that's why you get the same answer, right? So, in And this is exactly what this illustrates. So now I'm not taking the weights that lead to the Frobenius number, but I'm just taking length 1. As so on the left-hand side, you see a distribution of the diameter of a random directed circular graphs, where I choose the metric to be just 1 for the edges. And it's the same picture that we got for the Frobenius numbers, even though there will be a different, so this would be the same distribution. Okay, so that's
so many distributions look like that.
Why do they look like this?
Lean to the right, sort of.
Yeah, because these tails, they come from the cusps. So if you think of the space of lattices in 2 dimensions, that's just a modular surface. It's a unitangent bundle. So if you pick a random point, you pick it in here with respect to the Riemannian measure, the x, dy over y squared. Now, the things that we get are certain functions on the space of lattices, right? The diameter will have a limiting distribution of a certain function that lives here. And this function will grow in the cusp. So when you are interested in the tails, you are asking, what is the measure of points in your modular surface for which your function is larger than something? And that will give you a measure of the cusp. These will only grow in the cusp. And so, when you do this calculation, you find that you get an algebraic tail. Algebraic tail.
What?
Algebraic tail, not exponential. Algebraic tail.
The measure goes down exponentially fast.
That's right.
So that's not the difference.
But the function is growing at the same time. Okay, so the function is growing. So the way you go into the cusp is slow.
Algebraic.
Yeah.
So it's growing exponentially fast.
Yes. No, the function is, well, it depends on which sort. The function will be growing in the cusp like some power of y. And of course, the distance from a point here to a point y, you know how to calculate that, right? So that's the relation.
It's algebraic and y exponential.
Exactly. So that's all. I hope I've given you, my point was just to give you a snapshot. What is measure rigidity? What is a homogeneous flow? How can you translate the problem by giving you these examples from the original problem into a problem of homogeneous flows? Then you need to prove some equidistribution results, which can be difficult. I've glanced over this. I haven't really showed you how you prove these kind of things. But that's sort of the bread and butter of ergodic theory, right? Then you solve this equidistribution theorem and you get a solution to your original problem. And I just want to highlight again that a lot of people, including, as you've seen, Bourgain and Siné, tried these kind of problems using analytic methods. And they couldn't get the answer because the error terms were always too big. In low dimensions they could, in higher dimensions they couldn't. So, thank you very much.
More questions?
So why the ergodic theory is so much more powerful than analytic?
Well, as I tried to explain at the very beginning, the reason here why it works is because we have a classification of all possible limit points of whatever random variables we look at. And this classification tells us that these are extremely nice objects. It wouldn't be so helpful if our limiting distributions would live on some contour sets. Because then it will be hard to understand which of those guys will survive and which guys won't survive, because they're rigid in the sense that they live on nice embedded submanifolds. If you look at your sequence of probability measures that become equidistributed, you can rule out those guys that will be transversal most of the time to the potential candidates. So you can rule these out. They simply don't accumulate enough mass on these nice submanifolds. So then the only thing that can survive, that's the usual observation, is a harm measure. Full harm measure. Okay. You never ever calculate the rate of convergence.
If you look at the groups of this ergodic distribution results, then it becomes simply translated to some analytic methods.
No, absolutely not. This is the big challenge now. People try to make Radner's theorem effective on trying to establish rates of convergence in some cases. But all what I've shown you is at no point you have a translation into some analytic counterpart. Never, because you only always argue with the limit. You say, let's look at a convergent subsequence. These are the possible limits. Let's rule out the guys that we don't think are the right answer. You always only argue with the limit and the invariance properties of the limit.
So they were very common. The next problem that you can translate is language and key.
Since I'm being recorded,
I'll pass on this.
This is sort of a longish comment, I apologize. Because tomorrow is the Lean Appreciation Day, there's going to be a thing in New York. I'm just thinking, in the 70s, he was doing a Bourbaki report outside his field on a very deep theorem of the Shelter-Man, which is showing the Weil theorem works for nonlinear Isomorphism with a certain and I was going to IHS, and I saw him in his office sort of pulling his hair out. And he said he had done the whole proof, and there's a missing piece. It can't be done. Yes. Anyway, the way it settled down is it can't be done constructively. He understood all the constructive steps. And the ergodic theorem gives you a non-constructive extra piece of information which makes the proof go. So in fact, in that situation, you cannot make it constructive, because the lead says so. So I would not be too, there might not be these constructive interpretations if you're really using the ergodic theorem. Isn't that? I was once arguing with Gromov, sorry, this is a little longer, but he makes very provocative statements. The statement you make at the time is there is no theory of dynamics. Like there is a theory of complex variables and stuff like that. So I was trying to look for counterexamples, and finally I said, the ergodic theorem. That's not a theorem. The reason it's not a theorem is it doesn't give you an estimate on the answer, so it's a meaningless answer. You have to wait longer than the life of the universe for it to converge. It doesn't really give you anything. Anyway, this constructive issue is not trivial.
Other questions?
Yeah.
Or comments? Let's thank the speaker.